Okay, so when we take a look at this double integral, we've got the integral of 4xy plus 1 dy, where y goes from 3 to x, and then dx, where x goes from 4 to 6. So literally what I just said, right, we heard y goes from 3 to 6. So in other words, one of the things that we can see is, well, y then is greater than or equal to 3 and less than or equal to x. So y goes from 3 to x. And then with that constraint, then in terms of x goes from 4 all the way up to 6. So what we're actually doing is these bounds, these double bounds, are defining a region. So this defines a region that we usually call R. So sometimes how we draw this integral is we might actually write that this is the integral, a double integral over a region over R of some function. So say doing the function of 4xy plus 1 dy dx. So we've got this two variable function, a space function, but this is the region in the xy plane that we're integrating it over, which is kind of cool to think about. Now graphically what this is going to look like, we can actually put this on the graph, right? If I think about, well, where is y equal to 3? Well, it's on the line, y equals 3. So we've got y equals 3 here. And then, well, where is y equal to x? Well, it's on the line, y equals x. So if we draw that line in here, what this says is that my y variable vertically in the region, we're going somewhere from this horizontal line up to this slanted line, y equals x. We're somewhere in this region, and then what happens is my secondary bounds, my bounds on x, kind of give me then the horizontal, where am I pinching that region in on. So then x is going to go from 4 over to 6. So if we draw where those are, x equals 4 and x equals 6 are both vertical lines. So really my region ends up being right here. Is that a trapezoid or whatever? So y went from 3 to y equals x, from this curve, this function, to this function. And when we looked at that region on the horizontal bounds, where then we restricted x. So these double integral bounds are always defining regions of the space. So that's why my exterior bounds should be purely scalar, or at least constant in terms of our other function, because notice I've already defined where that function goes from and to. So now really we just need, in terms of, so we said y goes from 3 to x in terms of x. So now in terms of that, we then look at that, where x can vary from 4 to 6. So we get that full two-dimensional region of space in here. One of the cool things and application of this that we can use is we can use this to find areas of two-dimensional space. So same way that we did last time. So back in Calc 2, was it? We found areas between curves using a single integral, where we had to take a look at those two functions and subtract them. We can now find areas between curves using a double integral. There's just a different way to do it. So for example, if we wanted to say find the area, let's say under y equals the square root of x from 0 to 9. Well, if we draw that picture, we'd be looking at this region, right? This is y equals the square root of x. That's what the question is asking us to look for. If we think about what we just used, well, we can now represent this region using a double integral, using two sets of bounds. We can see the y variable We could choose that one to be in terms of x, so we could go from curve to curve. So it's almost like looking for that bottom curve, top curve. So it goes all the way from the x-axis, which would be 0, up to the square root curve. And then we want to look at those two curves on the bounds where x goes from the origin, which in this case is 0, all the way over to 9. So what this does is this is R. That's our region. So when we set up a double integral, we would first integrate with respect to y, and then with respect to x, because notice my y variables went from function to function, and then my x variables go from number to number. So my y variable is going to go from 0 to square root x, and then my x variable is going to go from 0 to 9. Now there's a question of, well, what goes on the inside of this? It turns out if all we're looking for is the area of a two-dimensional curve, then the integration, what we're going to put inside is just a 1. So we're just going to integrate 1 with respect to these bounds. And we can kind of see why this works, because if we think about what's going to happen from there, what we're going to get, well, when I integrate 1 with respect to y, 1 is just a constant, so that's going to bump up to a y. So it'll be a y, and that has the bounds 0 to square root x. This is still inside of the integral from 0 to 9 dx. So this gives you a little bit of an idea of kind of how to write these double integrals, just a smaller example. When I then evaluate that integral, well, notice I'm going to plug in the square root of x into y, which just turns into the square root of x. And then I subtract off plugging in the lower bound, which in this case is just minus 0, which goes away. We just get the integral from 0 to 9 dx, which if we think back to how we did this in Calc 2, that's exactly how we did it in Calc 2. And even if that lower bound hadn't been 0, right, we specifically in this one want the area under this curve, which means just integrate that function with respect to on these bounds. Remember when we wanted the area between curves, all you did was top curve minus bottom curve. But that's exactly what would happen here, right? Into y, we plug in the top curve, and then we subtract off plugging in the bottom curve. And we're always just going to get a y here if we integrate 1. So we're always going to get what we want, which is pretty cool. So then if we finish up that one, we can see what the area would be. We'd integrate square root of x and plug in those bounds. So I'll let you finish off that one. But this is how that idea works. So what we can do at this point is take a look at a few different examples and try and think about how this looks for finding area between bounded curves, and then also how we can take a look at practicing some other double integrals. So we'll hop back on here in a minute.